So we're now going to take a look at another case study that will illustrate the structured task scope stuff we were just talking about. And we're going to show both the shutdown on failure and shutdown on success nested subclasses in this example. It's a really fun example. All the tasks in this case study are CPU bound, which means they're not blocking on I/O. They're just processing things and doing stuff in memory. And this particular example, just for fun, is going to use the classic Java features rather than using Java sequential streams, just because I felt like it. Also, there's a school of thought that says the structured concurrency stuff is really designed for people who don't want to have to understand functional programming. I'm not quite sure why they would not want to understand that, because it's pretty cool. But for those of people who don't like to use functional programming, this is a non-functional programming way of using Java structured concurrency. So we're now in the ex3 project in my Loom folder in my GitHub Live Lessons repository. And let's go ahead and take a look at this particular piece of code. So this example is going to show how Java structured concurrency works, where we're going to split things up into subtasks within a task. And we're going to show both the shutdown on failure and shutdown on success ways of doing things. And you'll need Java 19 and Gradle version 7.6 or later in order to run this test. So the test comes in here. We parse any command line options we might want to give, or we just use whatever the defaults are. And then we're going to go ahead and demonstrate the structured concurrency on the number of elements that we're going to be processing here. And we can override those things as we see fit. So here is demonstrate structured concurrency. It takes a count. And the count is the number of random big fractions to do for our tests. So once again, just creating large random things to take a while to run, thereby motivating the use of concurrency. Obviously, in real life, you're likely to do something more interesting than checking to see whether multiplying and reducing random big fractions, but we just need something that burns CPU time. So here's how this works. We start out by making ourselves a try with resources block for a structured task scope shutdown on failure variant. So remember, that's kind of the invoke all style, where everything's going to run and we're going to wait for all the stuff to finish. We're then going to go ahead and make ourselves a new results array. And because we're sticking here with Java 7 style features as opposed to Java 8 and beyond, we're going to say new array list. I want an array list of futures to big fractions. I could have said list future big fraction results equal new array list, but I decided just to do it like this for kicks, just to do it a little differently. So we have ourselves an array list of futures to big fractions. And then what we're going to do is we're going to go and generate a bunch of random big fractions. So as usual, though this is kind of fun, we're going to use a stream factory method called generate. And generate is given a supplier lambda, and it's just going to call this thing forever. But we don't want to generate this forever. We're going to limit the amount of random big fractions we're going to make to the number of items passed in here as a parameter. So we're going to limit to count items. And we're going to return a list of these things. And make big fraction is just a little helper method. I've probably shown this before, which makes a very gigantic big fraction with a very large numerator and a smaller denominator. And then it makes a big fraction out of the numerator and denominator, which are big integers. And you can decide whether to reduce it or not. We are not going to reduce it, pass in false, because we're going to do that concurrently, because that takes a while. So we're going to make a bunch of these things. Let's say we're going to make, 100 or whatever of these big fractions randomly. And then what we're going to do is for each big fraction, we're going to go ahead and add the results to the results array of forking off a new virtual thread and reducing and multiplying that big fraction, reducing it first, and then multiplying it by this constant we pass in, which is another big fraction. And we'll look at reduce and multiply in a second. But what I want you to observe here is we're forking a new virtual thread. So as many of these things, let's say we have 1,000 of these things or 10,000 or whatever, we're going to have 1,000, 10,000 virtual threads running. And we're going to stick the results at the end of this array list. And you'll notice it's an array list of futures to big fractions, because that's what gets returned from fork. You get a future back to whatever result you're going to be computing. So let's just take a look at what we're computing. This is sort of neither here nor there, just again to burn CPU time. But we take one big fraction and we reduce that big fraction. So if you have something like, 18 thirds, it'll turn it into the appropriate reduced fraction instead of 18/3. Or if you have 55/11ths or something like that, it'll reduce it to be 5. So then we're going to go ahead and multiply the reduced big fraction by this other big fraction. Again, nothing too interesting, just there to burn compute time. So all those things are going to go off and run in parallel. And then we're going to call the join method. Join is this barrier synchronizer that waits for all the threads to finish or for the task scope to shut down because an exception was thrown. In either case, this doesn't return until either all those guys are done or there's been a problem. If there's been a problem, like the first one that has a problem throws an exception, we're going to propagate that exception. Otherwise, by the time we get here, we know we have a list of futures to big fractions. And even though they're futures to big fractions, they're all done because we wouldn't have gotten here if they hadn't finished. So what we're going to do then is we're going to sort and print that list. So let's take a look at that. And this example is kind of fun because it's going to demonstrate how to use the shutdown on success variant of structured task scope. So you can see here, we say new shutdown on success. I could have said new structured task scope dot shutdown on success, probably should have, but it's verbose. So we make one of these guys, and we tell it what the return value is going to be when this thing is finished. And it's going to be a list of big fractions. So we're going to convert a list of futures to big fractions to a list of big fractions. This is where things get a little bit ugly with Java structured concurrency, this mode of Java structured concurrency. And I don't like it. I'm not sure what exactly to do about it other than to use other concurrency mechanisms in Java, which we'll talk about later. But the long and the short of it is we've got a list of futures to big fractions, and we want to sort them. And we want to sort them with quicksort, and we want to sort them with heap sort. But they're a list of futures to big fractions. And it's probably possible to write a generic sort algorithm with the right comparator that will do this, but it's really a pain. So what I'm going to do instead is I'm going to take this list of futures to big fractions, and I'm going to turn them into a list of objects, so a list of big fractions, as opposed to futures to big fractions. And to do that, because it's kind of a messy thing, I wrote a little helper method here. It's in a utility file called futureutils. And what it does is it takes the list of futures to type T, and it turns it into a stream of futures to type T. And then it goes ahead and it uses future result now as a method reference. So what that does is it basically converts the stream of futures to T to a stream of T. And we know those things were done, so it's not going to block. It just has to be done. We get rid of anything that happened to be null. There probably isn't anything, but if there was, it would get rid of it. And then the last thing we do is we convert the stream back to a list. So now we have a list of objects of type T that were converted from a list of futures of type T. So just some additional ceremony that has to be used when you're dealing with the results of these fork operations. So we're going to go off and sort with heap sort, with quick sort. When we're done, we're going to join. So whichever one finishes first, we're going to be done. And in this case, I'm being optimistic. I'm not checking to see if there's an error. Probably should. And then what we're going to do is we're going to say scope result. Dot result is whichever one finished first. So whichever heap sort or quick sort finished first, the shutdown on success mechanism cancels the one that is not done yet. And then we take that result, and then we go ahead and print the results as mixed strings. So this is illustrating, this little example here is showing off both the shutdown on failure model, the invoke anything that we did when we were trying to do the reductions and multiplications of all those big fractions. And then this one shows the shutdown on success, which picks the first of two when it's done. So that's the invoke any model. So let's go ahead and run this just for kicks. And I forget exactly how many of these things we have. It's probably a fair number. So off to the races, doing the generation of the big fractions, random big fractions. Now it's doing probably the multiplication of all those things in the background using virtual threads for each of the computations that we're doing. You can see it's taking a while, so I probably gave it a big number. And there we go. So you can see, I think we had maybe 20. You saw how long that took to run. That's because we generated astronomically gigantic big fractions. You can see how big those big fractions are. So they went off and were reduced and multiplied. And then we sorted them with heap sort and quick sort at the same time. Why not? I got 10 cores. Have fun. They're just sitting around doing nothing, so I might as well take advantage of them. And then you can see it prints them out in sorted order when we're all done. OK, so that's the end of the ex3 example.